In this example, we're given a right circular cylinder with radius r equals 10 feet. The depth of the cylinder is 8 feet, and it's filled with water up to 5 feet. The water is to be pumped out the top of the tank. Find the work required to pump all but 1 foot of water out of the top. Okay, solution. First, we want to recall note number 130, and that's the one that says that the work done by a force F to move an object from position x equals a to x equals b is W equals integral from x equals a to b of the force f of x dx. So this is a variable force. So we're going to use that. First, step one, let's do a sketch, a formal sketch of our right circular cylinder. We have a circle at the top, basically a circle at the bottom, and it's a tub. And we're going to put the x-axis right down the center, and we're going to put the origin at the bottom. Now, we don't always do that, but for convenience we did it. Now, we're going to label the x-axis as the vertical axis and the y-axis as the horizontal axis, which is swapped. That's different than what we usually do. At the bottom, at the origin, we're at 0. Then we're filled up to 5 feet of water, and there's a maximum depth of 8 feet of water, and the radius of this cylindrical unit is 10 feet. Now let's analyze what we have here. Consider an arbitrary disk of water located at position X in the cylinder. And let's say that this disk has thickness delta x, because we'd be measuring that thickness vertically, and the x-axis is our vertical axis. So let's get a rough sketch of what this disk of water would look like at this arbitrary x position. It would have thickness delta x, looks like a quarter, and its position is at x, an arbitrary x. And the radius of the disk happens to be exactly the same as the radius of the cylinder. It's still equal to r equals 10 feet. Now, if this were a cone or this were a hemispherical dish, it would be different. But for this cylinder, it's 10 feet, just like the original cylinder. Now, the force for the water on the water is rho times g times a times d. Rho is the fluid density, g is the acceleration due to gravity, a is the area of the disk face, and depth, d, that's the depth of our arbitrary disk in the fluid. For this problem, we have water density, rho, is equal to 1,000 kilograms per meter cubed, while gravity is 9.8 meters per second squared. But that's only true for Newtonian units, and we're not using metric units here. We're using United States English units. So for our problem here, we multiply rho, water density, times g, acceleration due to gravity, and that for our units is 62.5 pound-feet cubed. So that is what we're using. Rho times g is 62.5. Step 3, we will now find the depth of our disk. Our disk is located, as we said earlier, at position X. And it must be raised 8 minus x units or feet to pump it out of the top. All right, and you can see this by just looking at the picture. Our disk is located at x, but there's an entire value 8 in the depth of this tank. So to move it out, each disk has to be raised 8 minus x units. So the depth is 8 minus x. And step 4, find the area of the disk face. Well, we know in general area equals pi r squared. In this case, the radius of our disk is going to be 10, as we discussed in step 2. Therefore, the area of the face is equal to pi times 10 squared, which is pi times 100. Step 5, find the force. Okay, the force on the disk to move it is rho times g times a times d. And since we're using English US units, rho times g is 62.5. The area is pi times 100, and the depth of the disk is 8 minus x. So that's our force. So step 6, our last step, to find the work to pump the disk, to pump the water out and move the disk from level A equal 1 to level B equal 5 on the x-axis. In other words, to pump all but 1 foot of water out of the top. Recall, that's exactly what they asked us at the beginning. They want us to pump everything but 1 foot of water out of the tank. So the work to do that will be equal to, well, we know it's equal to the integral from x equals a to x equals b of the force f of x dx. And we calculated everything we needed here, so it's equal to the integral from x equals 1 to 5 of rho times g times a times d. That's called the hydrostatic force, by the way, dx. It's equal to 1 to 5 of 62.5 times pi times 100 times 8 minus x dx. And we just pull out the 100 times 62.5 times pi in the front because it doesn't depend on x, and we integrate 8 minus x dx. That gives us our antiderivative, which we integrate from 1 to 5. We get 125,000 pi. And the units will be in feet pounds, but that's not really the answer. For us, the number is what's important. 125,000 times pi.